And today it's my pleasure to introduce Professor Karen Flack from the US Naval Academy. She is in the Department of Mechanical Engineering at the US Naval Academy, where she was formerly the head of department and has held several roles there. She graduated her bachelor's degree from Rice and a master's degree from UC Berkeley, and then a PhD from Stanford before she moved to US Naval Academy, I think in 2004 or 2005. I mean, she's on the editorial board of International Journal of Heat and Fluid Flow, Experiments in Fluids and Flow, Turbulence and Combustion. And she's a fellow of American Physical Society in the DFD and has won several awards for various things. And today she's going to talk to us about prediction of drag for rough wall boundary layer flows. So over to you, Karen.
Great, thank you, Bharat. It's a real pleasure to be here, and I was very thrilled to have the invitation to speak with you all. So I'm going to share my screen real shortly, but I want to give a special hello to Ian Castro, who I saw is here. He's been a tremendous mentor to me over the years. So thank you, Ian, for joining us today. It's really, really nice to see you. And so I'm going to give a little talk about roughness, and hopefully if you have some questions, put them in the chat. So I'm going to talk about how we predict the drag on rough wall flows. And this is a question I've been thinking very, very hard about for a lot of years. So I have been working with a colleague, Michael Schultz at the Naval Academy for many years, and we've kind of been tackling this roughness problem head on for a while. This work is also going to highlight some of the work done by Julio Barros, who's currently at Okinawa Institute of Science Technology when he was here for a postdoc. He was a tremendous asset to this research. All right, so this is a big deal for the Navy because drag causes a lot of an increased fuel costs and performance penalties. And this was work done by my colleague Mike, and he published this in Biofouling back in 2007. But basically, what is the kind of percent increase in ship shaft power if you have roughness? And if you had a hydraulically smooth surface, there would be none, right? But it's not hydraulically smooth. Even paint can cause a 2% increase in kind of the shaft power. And as you go up with kind of other biofoulings like slimes, the light coating of slime, and here's a heavy slime, you get up to weeds, and you've seen these these kind of marine kind of biofouling things on ship, up to kind of barnacles and calcareous foulings. You can see an extreme penalty. But the interesting thing is, even if you have just a very light coating of slimes or something on the ship hull, for this FFG, which is a typical Navy destroyer at 15 knots, it's causing a 10% increase in drag, which is a significant fuel cost and a significant performance penalty. So it's a very important thing to the Navy, and it's important for all sorts of industrial applications and atmospheric boundary layer applications and such. And so we've been looking at this problem not only from the flow physics, but then how to practically we create kind of engineering models in order to account for these. All right, so this is what we've been using for a long time, and I've always been fascinated with this diagram. Was fascinated with it as an undergraduate, so it's kind of I think it's fun that I've been studying it. Probably the reason I have been studying it. The fact that we can scale things in non-dimensional versus non-dimensional always really I thought that was interesting. But this Moody diagram is a very important diagram for estimating the drag, and basically this idea of an equivalent sand grain roughness height. And we have, a frictional drag coefficient versus Reynolds number versus this kind of non-dimensional roughness height of the diameter or the hydraulic diameter of the duct or something, or the diameter of the pipe. And the equivalent sand grain roughness height is the height of Nicarazzi sand that causes the same frictional drag in the fully rough regime. Now that's a lot of things that go into that. It's more complicated than it looks. Basically, it's based on a monodispersed sieved sand height. And you have to be in this fully rough regime, often called the wholly turbulent flow regime, basically where the frictional drag is independent of Reynolds number. So it's flat here. And whatever your surface is, it has the same drag as that height of sand grain, equivalent sand grain roughness height. So, you see diagrams with it listed, and it's a little bit ambiguous. First of all, it looks like it's just a physical height of roughness. it's not, it's a hydraulic scale. You have to have run a test to know what this equivalent height is. And there's often ranges and, you know, it's confusing how to use it basically. But the important point is it's not a physical scale, it's a hydraulic scale. You have to have run a test or now a simulation to determine what the equivalent height is. And so basically that's what we've been looking at. How do we find out what this equivalent height is? All right, so I'll show you a little way that you can get it. First of all, it's very, very reliant on the fact that we have outer layer similarity. Outer layer similarity is the idea that the smooth and the rough wall boundary layer behave similarly when scaled, basically the correct scaling on basically the friction velocity and the boundary layer thickness, that they're similar outside of a region near the roughness or outside the roughness sublayer. We call this the outer region. And for the mean flow, basically it looks like a shift in the log law, a downward shift, which is basically a momentum loss. We call this delta U plus, basically the roughness function, the shift downward in the log law. So you could go do a lot of boundary layer profiles and get a delta U plus versus a roughness Reynolds number now, where the roughness Reynolds number is based on a roughness height and the friction velocity. So this is nominally what it might look like for a painted surface or a scratched surface or a sand grain surface. And they all have a similar kind of trend. They start off hydraulically smooth. Basically, there's no influence of roughness until you hit a certain roughness height. And then you go through this transitionally rough regime. And at some point you hit the fully rough regime, which is basically it asymptotes to a straight line. And, you know, for a given surface, you do this, you can come up with a roughness function as a function of this roughness Reynolds number. And you could go put that in a wall function, go to RANS or wall modeled LES, and off you go. So you have, you know, if you have to run the test, you get this roughness function and you can then model it thereafter. If you use the equivalent sand grain roughness height as your scale and your roughness Reynolds number, all of them collapse in the fully rough regime. And so then in the fully rough regime, if you have delta U plus as a function of the equivalent sand grain roughness height, you know, plus, then it's valid for any roughness in the fully rough regime, okay, that has that KS basically. And so this is kind of where we're after. We're going, then you can take that to wall functions, you can take that and put it in your simulation tools. The other thing you can do with this, which is very important, and this also relies on this whole concept of outer layer similarity, is you can take lab scale results to full scale, which is, you know, how we figure out what the drag penalty is on a full scale ship. And you can create these Moody type diagrams, which, since I told you I was fascinated with that, we'll see one in a minute. So this is how we go from lab scale to full scale. And this is a very clever idea by Granville, who was a scientist at Carter Rock for the Navy. This is how to get the overall frictional drag as a function of basically Reynolds number based on a length of a flat plate, but it's used for ship scale. You have your smooth friction line, you shift it with a function of this roughness function that you've determined somehow. And then basically where this intersects this line of constant L plus, which is right here, you can figure out then what the overall frictional drag is for the ship. And if you do this a lot of times, you can come up with a frictional drag coefficient as a function of basically the log of the Reynolds number, and it looks like a Moody diagram. Only in the fully rough regime. You see, I don't really know what's going on in the transitionally rough regime because what I'm doing doesn't apply to the transitionally rough regime. I don't know what's going on there. But it comes up with this equation. I made it look like lines, so it looks like a Moody diagram because that was very pleasing to me. But basically equation of KS over L, the equivalent sand grain roughness height as a function of length for a flat plate covered with a given roughness that has a given KS. There it is. So this is all great, except there's a missing piece of information. We don't know what KS is unless you run a test, which is expensive or maybe becoming less expensive with simulation technology. But the whole goal now is how could we figure out KS as a function of surface topography and not have to do our hydrodynamic test or our simulation? What if there was some measure of the surface distribution that we could use in order to come up with equivalent sand grain roughness height? So we've been basing our ideas that we're working on this very, very clever idea by Musker back in 1980. He thought that what if we use basically the scales based on the moments of the probability density function, such as, so you have basically a PDF of the amplitudes of your roughness heights. You take some sort of map, surface map, or some basically, line scans, and you come up with this distribution of what the height is. And you look at statistically what's the RMS of that. So different moments, the skewness of this, if it's positively skewed, that means the surface has more, peaks than valleys. If it's negatively skewed, it has more valleys than peaks. So it's got divots instead of, protrusions. The flatness is kind of a measure of distribution. And if you have like large asperities on the edges, is a measure of the flatness. So there's a lot of surface information that's carried in these statistics. So Musker proposed that this was a good idea to how to represent it. So we looked at, this was from 2010, we looked at the available literature of the time, which was some packed spheres, sandpaper, gravel, honed pipes, commercial steel pipes, closed packed pyramids that we've done, scratch plates, and we basically came up with a correlation that worked fairly well for the equivalent sand grain roughness height as a measure of the RMS roughness height and the skewness of the probability density function. So 2-parameter model, those seemed to be the things that worked best. And it was for a large range. This is, the gravel up here, and then, you got your pipe down here. But, this looks good. It's a huge range, but you can see there's actually some pretty significant errors down at the lower end of the scale. So what we decided to do was really kind of test the robustness of this correlation with a lot of surfaces. And the other question is, what happens in the transitionally rough regime? This is really only valid in the fully rough regime. And not everything operates at fully rough. In fact, a lot of things don't operate at fully rough. So the transitionally rough regime is a very important part. So our idea was we needed to systematically modify the surface features instead of, just kind of getting what you get by throwing in different sand grains and using mesh screens and, gluing grit and divoting a surface kind of randomly, which we've all done. Well, not all of us, but for those of us who do roughness research, we've tried that. Now we need to systematically modify the surface. In order to do that, we decided that the easiest way to get really high quality measurements of friction curves was to build a flow channel. So we have this high Reynolds number channel. Here's the idea of it. Look at the top part. The bottom part is another flow facility we use. But water is kind of pumped up through, kind of flow conditioning devices into this 8:1 aspect ratio channel. 1 inch by 8 inch nominally, or the metric equivalent of that. And we have a smooth upper and lower wall, basically for the first half of the test section. So we get fully developed turbulent flow. And then we put in a roughness on the top and the bottom for another distance, about half the distance. And we have some optical windows here at the end where we've tested to make sure that it was, again, fully developed channel flow by the time we take our pressure drop measurements. You can see that we get some very high Reynolds numbers. You'll see very good friction curves. And we were so happy with this channel, we've actually published the smooth wall data for this in a physics of fluids paper. So this is where our roughness goes on the top and the bottom. The side walls, the 1 inch, side walls do not have roughness on them, and that's where we take our pressure drop measurements. We do it multiple times. We think we can get the wall friction very accurately. Okay, so the whole idea was systematically changing the scales. So instead of creating the surfaces, by gluing something on, we mathematically create them in MATLAB and then use the 3D printing technology to create the surfaces with the distribution we want. The first one we used was basically surfaces that had a power law slope power spectrum, where we can change the wave number and the power law slope to get to kind of what we want. And we created them on a very high resolution 3D printer. You see the 16 micron elevation resolution. And then we measured them on a high resolution optical profilometer to see what we got out. And we don't exactly get out what we put in, but you can kind of see this is what we generated and this is what we measured, and we can't capture all the scales. There's some spatial filtering that goes on. Mostly in our printing, we do feel that our profilometer does a very good job of telling us what we got. So we put these surfaces in where we had increased the negative power law, basically. And this was a very interesting surface. You can kind of see the heights increase as the power law goes more negative, or the absolute value of the power law increases. Heights increase. The skewness is, slightly positive skewed, a little bit negatively skewed. It's not that much change in that. The effective slope we'll talk about. That's basically the average slope of the features of the flow. That becomes an important parameter. But if you look at these surfaces and you look at the heights, you'd think, well, the average height, RMS height, this is a peak to trough, basically some measure of the highest peaks and the lowest troughs, is the largest for this negative p equals negative 1.5, which is this one. However, that is the red square. It has the least amount of frictional drag. Okay, this surface right here has the most, and it has the smallest features. Okay, so something has to do here potentially with the skewness, or what we really think is that there's large wavelength features in here that are kind of, the wavelength of these features really matters. Basically, the slope of these features matters quite a bit, and that potentially there's scales that don't contribute to drag. I think these are sharp features. These are kind of undulating features, and the sharpness of these features causes an additional frictional drag. So our conclusion from this was long wavelength features do not contribute significantly to drag, and our choice was to kind of filter them out as a scale of 10 times the peak to trough roughness height. Our next, I'll get to the results of these in a little bit, but our next surface we said, well, was let's try a Gaussian distribution, PSD, power spectral density distribution. And you see we did the same type of thing, generated, profiled, and this was the equation where we could adjust the wave number and control the shape of the spectrum here. We tested these. The two things we changed, we said, well, let's change the RMS height. We could dial that in basically, holding the skewness at constant at 0. And you can see again, we have a little issue with our effective slope. We didn't quite get that controlled. But so we're increasing all the kind of height parameters. And this time fluid mechanics acted as we expected, that if it has a larger roughness height, it has more drag. So this worked in that way. And you can see that, it goes up significantly with roughness height. When we held the roughness heights constant and increased changed the skewness. So let's look at this one. This just kind of shows what a negatively skewed surface where the reds are pits, and this shows a positively skewed surface where the let's see, the red is height and the blues are pits, and anyway, these one's pits, one's peaks. That's the idea there. And we changed the skewness from being rather negative to rather positive, going through 0, which we had before. And so when you increase the fact it's skewness, meaning it has large peaks, it goes up as well. And in fact, this surface here with the upside down triangles is a very peaked surface. Statistically, it has many more peaks. And the other ones, if it's pitted, it goes a little bit different. It's a little bit lower, okay, than actually the one with the 0 skewness. And all these heights are the same. So it doesn't change much on this lower distribution, but if you have peaks, it really goes up, which makes sense. We think there's some sort of flow filling basically that happens with pits, or some skimming over the surface. But when you have peaks, that's when you're going to get separation and vortices and all those things that, kind of transfer momentum in the flow. So if you put these all together, we'll see basically the height of the roughness matters. This red one is the lowest height with the 0 skewness, and so it increases with height, but it also increases with skewness, with basically, negatively skewed surfaces not behaving that much differently than the 0 skewed distribution. So there's some sort of flow filling. All right, but here's the test. We want to make this roughness function so we can come up with our equivalent sand grain roughness as a function of basically different height distributions. And what's nice is you know, first of all, we forced them to fit here, but in the transitionally rough regime, most of them actually fit together, except two that are different. One, which basically had the lowest height, but this also had a very, very shallow slope, And the one that had this downward triangles, which had very high skewness. So, okay, so in the transitionally rough regime, it's encouraging that a lot of them fit, but something's going on with these kind of outlier cases. All right, let's go back and test our original correlation. That was the point. Now we have more data. We also have some basically things I didn't show you. Grip blasted plate. Before we got our printer up and running, we decided, well, let's go one more try at, you know, creating systematically varied roughness kind of randomly. And we shot a bunch of grit at acrylic plates and made them pitted. So those are all sitting down here as well. Put it on here and you can see, well, the Gaussian ones really don't match. The other stuff, it's hard to know what's going on with, but let's just blow that up and show just how badly it does. Okay, so our correlation is not really working. You can see these surfaces just are not falling, are not being scaled. The rest of the stuff somewhat, but still there's a lot of error down there at the low end range. However, if you decide to separate them by skewness, basically whether it has lots of peaks or lots of valleys or, you know, a Gaussian distribution, we do a pretty good job of being able to capture this. Okay, it's not perfect, but the point is that it matters whether or not there's peaks or pits, which intuitively to us is, you would think that would make sense. And we do a pretty good job. So we published new correlations, you know, basically that was the same form, but if the skewness mattered, you have a higher power here. If the RMS mattered, you know, you have a higher number, you have a lower number there. And if it's zero skewness, well, it's just a matter of KRMS. Okay, that is one set of experiments. Another set of experiments we did is we decided to test basically ship biofouling slimes and see if how much of a drag penalty they actually caused. So we created a slime growth facility where we grew slime on plates. It was very exciting. It was, well, anyway, we had a good time with this. Basically, we put plates on a drum and we rotated that drum in water just, you know, constantly. And we turned a light on and we turned a light off and we heated it. So we were simulating basically a ship underway. And the reason that we wanted to rotate and kind of move it was, so we wanted the slimes that grew when the ship was moving, not the ones that grew when it was, you know, sitting in port or in dock or something. Those slimes would slough off. We wanted the tenacious slimes that stay on. Okay, so we were looking for those tenacious slimes that hang on and grow under shear. So we did this and basically used instant oceans. So we had seawater and we had to fertilize the slimes because they're organisms that needed to grow, so they needed food and such. And so for a long time, you'll see we rotated this drum on and off and turn on the light and off and kept it going and grew our slimes. And this was the type of slimes we had. They're diatoms. We have a biologist here who told us what slimes we had. And we tested them on 3 types of ship paint: a silicone fouling release, this fluoropolymer fouling release, and then this specimen C, which has a slime release. So that's kind of the special one, made by a ship paint company who coated them for us. And after 3 months of exposure, we put them in our channel. We ran it up to the highest shear we could, and then put it back down. So we'd slough off anything that was not tenaciously going to stay on. And then we did our experiments. This is what it looked like at the end. We feel like we got everything off that was going to come off by shearing it at the beginning. And, you know, all we can really measure basically on this is the percent coverage and the thickness. We're not doing quite a sophisticated analysis of our PDFs of height distributions. But you'll see it's patchy and there's some clumps and there's regions that are and aren't covered. But we measured the height with a paint gauge kind of measurement technique. And that was what happened. And we also had an acrylic control, something that didn't have the paint on it. Okay, we did it. We had some that we stayed in for 6 months. So we took some out after 3 months and another set after 6 months, and we got kind of different distributions, and we did the same kind of measurements of those. So this is what you would, if you saw this maybe on your hull of your ship, you'd like, well, it's probably about time to clean it, but it doesn't look terrible. I don't see any barnacles or kind of grassy stuff growing on it. It's how much drag could that possibly cause? Well, we'll find out. There it is. Okay, so we can get the friction coefficient by doing these friction curves. We put them in our channel, and specimen A did worse. Specimen C, which had the slime release coating on it, did best, and did the same thing after 6 months. And again, specimen C is really kind of doing whatever chemically it needs to be doing to keep the slime growth off. Make a roughness function of these, because that's what you want. You want to get basically the roughness function is a function of the roughness height. We use the average roughness height for this one, and you can see they don't collapse. They don't collapse at all. In fact, some of them kind of tail off, which is an unusual kind of behavior. Normally they kind of need to asymptote. This one is kind of tailing off. All right, only the ones that reach fully rough can you get a KS. Okay, I can't stress that enough. You cannot get KS unless you have data in the fully rough regime. Okay, so I'm not using all of these because some of them didn't get fully rough. They kind of, they don't get to be independent of Reynolds number. So the ones that did reach fully rough, which was only a few of them, we came up with, this very sparse data set, kind of effective KS, which is based on percent coverage and height. And it turned out you needed to have a really high coverage in order for them to kind of be in the fully rough regime. This one had 49% coverage. This one had 27% coverage. What's going on less than 25% coverage? It's who knows? Like, we're getting these things that trail off and don't kind of come to that asymptotic behavior that we expect for fully rough. It is interesting to note, though, that they all kind of pop off of being hydraulically smooth at KS plus or K effective plus of 2 to 3. Okay, so there is a point where they're hydraulically smooth, and then it kind of pops off to have some roughness effect. Okay, so now we'll go back to our Granville similarity theory and say, how much increased drag does this actually cause on a ship of given length that is covered with that representative roughness slime? And we take our results from the lab, we scale them up to ship scale using Granville's ingenious methodology, and there is our increase in shaft power at 15 knots for specimen A through specimen C in the control. So specimen C is doing a quite nice job, 1.5% increase, and specimen A at 6.3% at 15 knots. But still, that's a significant penalty in fuel and performance. And you can see after 6 months, the one that had more coverage, we were getting what we thought before, which was about a 10% increase for the one that had the worst amount of kind of fouling on it. Specimen C doing quite a good job. Okay. So that was a very interesting result for the Navy, because that did not look like a terrible amount of biofouling on their ship. Specimen A didn't even look like a terrible amount, and yet it was causing a 10% increase in shaft power. Mike has been working with the folks in the Navy quite a bit at actually changing their thinking about when to clean their ships, which is really important for this. Okay, I want to shift in another gear. And this is basically how we're getting to this idea of how to predict the scales. And I want to highlight a few studies that have come out in the last several years, because although we've been working on this, there's been a lot of people, including Bharath, who's been hosting this one. Some excellent simulations have come out. And I want to highlight this one basically from Thacker, Bussey, and Sandham. This was really a great a great study that showed that we could use DNS over realistic roughness to get this friction curve, because as I said before, you can't get a KS unless you can get up to fully rough. And they were able to go from hydraulically smooth to fully rough for a realistic surface. And that is a huge improvement in our computation, and just some very clever way of modeling the surface, and also just the ability that we've had to improve our modeling capabilities. Okay, the Melbourne group has been working on basically looking at tube worm fouling, and they've been able to do some nice work on getting roughness functions for tube worms. And that doesn't look like the roughness functions we saw before either. That's an unusual shape. It hits fully rough, but you know, this is a really hard problem, obviously. And you can see, you know, they've got high kurtosis, they're highly skewed, they're positive. They've got, you know, this effective slope. The PDF looks, you know, like a very, very high positive skew distribution. Some work has been done again in the Melbourne group of looking at some simulations over this kind of varying pipe walls. And what's nice about this study is they have this kind of minimal flow channel where they're able to get the mean flow velocity correct at kind of minimal computational cost. And they've come up with a correlation basically that estimates it as a function of the average of roughness height and the effective slope. And another group of Rugi in Germany, they came up with this idea of the 3-parameter correlation. KS is a function of KRMS skewness and effective slope. Okay, so the whole idea is there's several groups doing this. We're doing it for experiments and very, very clever simulations coming out for this. And one in MPMLE. Again, this is for like a realistic turbine blade roughness and some strand grain type roughness, and you can see their parameter space has to do with effective slope and this RMS kind of slope of the surface. So a slope parameter is important to this as well. And look at this. This is awesome. This is where we're headed. This is a data-driven approach, basically. You know, how can we use you know, machine learning basically to come up with a correlation space? And so at Michigan State, they've done this really nice work where they put in 10 parameters. I call it the N parameter correlation, but they put in 10 parameters which had, you know, basically these RMS, skewness, kurtosis, this effective slope parameter, some porosity parameter, and some other kind of things to come up with, you know, a weighting factor where they train it and then they get it. So I really think this is a neat way to go with the amount of surfaces you can put. And I will say that myself and Daniel Chung at Melbourne are putting together, this will be coming out shortly. We're coming out with a paper, we call it amongst ourselves, we call it the big table of roughness correlations, but a discussion of basically all the correlations that are coming out to try to come up to solve this problem, and the parameters they're using, the equations are coming up of how they're testing it. The whole idea is let's figure out where are we with this problem, and how can we go forward with it. And this is just a couple of pages we have a really big table of correlations, which will be nice. Also, I've been thinking about this not only with Daniel, but my colleague Mike Schultz, but Nick Hutchins. We wrote basically a paper for the annual review of fluid mechanics recently called Predicting the Drag of Rough Surfaceness. But one of our conclusions was that a predictive model needs a bare minimum of either a height, some measure of height of the roughness, the average height, the RMS, a peak to trough height, some measure of basically frontal solidity of the roughness, which these three are all kind of mathematically related. A density parameter, an effective slope, or a frontal solidity, and a planned solidity, basically, or skewness or solid volume fraction. Some measure of those needs to be included as a minimum. I'm not saying it's the right, but you really can't get it right without at least having all three of those in there. And the last thing I'd say is that the one other thing that we really need to focus on is most of the correlations have been for, you know, homogeneous surfaces. I mean, they're not completely homogeneous, but they're not patchy. basically what happens if you have a patch of roughness and then you have a gap and you have another patch of roughness. Or this is going to problem. So my next set of experiments, this is what I'm going to tackle, is I'm basically going to have two roughness. I'm going to have a milder roughness as a base, and then I'm going to have these kind of random circle distributions of higher roughness, and change basically the plan form density and change the kind of size of the roughness, and see how we can kind of come at this. And with the hope that I can, you know, what I'm trying to do and what Mike and I are trying to do is create kind of some experimental results to be kind of validation test cases, because we honestly think the way to solve this is simulations. And we're just trying to provide clever test cases for people to do some validation on and then move forward with that. I'm now going to give a plug to something that Bharath and I have put together with some help of a couple of our colleagues, Matthias Nielsen and Julio Barros, is this Roughness Database. The idea is we can't do this unless we have access to a lot of roughness data. We can't come up with these data-driven correlations or ability to test data unless we have the ability to access these. And so there's this Roughness Database where we're trying to kind of put all of the studies together, and so you can access this and do your own test of coming up with correlations for the equivalent sand grain roughness height. Be the sand grain roughness hero. Someone needs to do it. Doesn't have to be me. All right, the idea is that it's a searchable database. We have you categorize it, and so that folks can understand whether it's homogeneous or non-homogeneous, you know, boundary layer, channel flow, et cetera, simulation or experiment. And we have basically all the XYZ coordinates of the surface would be there. So you can kind of do your own simulation if you want using the XYZ coordinates of the surfaces. There's a MATLAB program to give you all the surface statistics. We have the surfaces, we have flow documentation as far as, you know, the Reynolds numbers and such of the flow, and also just something with the paper so you can access more information. So this is really a resource we want for the community to help us kind of solve this very important problem. So I'd like to highlight just a few of the state of where we are. First of all, I'd say predicting drag, there is hope. There is hope. I think we're getting much closer. The great news is that basically the simulation, the DNS and the LES are just getting spectacularly good at these problems. And, you know, there's been a lot of work on this. It highlights a few of these papers. Basically, we've had mathematically generated surfaces. We've had scans of real surfaces that are being used to create these. And there's also computationally efficient methods to determine the mean flow properties, which is very nice. The work of Chung and Farugi, basically the minimal channel, the low Reynolds number channel, allow us to just get a wide parameter space. And I think this is what's going to be needed. What's great is rapid prototyping techniques. 3D printing has allowed us to kind of systematically, you know, modify scales, which is hard to do with just kind of other methods. This kind of came along at the right time. So I've done some work with Mike and Julio in order to do this. And I'm very excited about these new machine learning and methods and data-driven algorithms that you know, is highlighted in this very recent paper that's come out. So the good news is now experiments and computations can investigate similar complex roughness. And you know, all the work we've done into learning about the flow physics and learning how to do really efficient computations is kind of coming together to solve this problem. And so I say we are at the cusp of making significant progress. It's been a real joy to kind of participate with all the colleagues I have over the years working through this problem. So I'm just going to stop right now and acknowledge basically the tremendous help I get at the Naval Academy from the hydromechanics lab. We have some beautiful facilities and some excellent technicians that help us. Also, we have a wonderful model shop that helps us do our work. The Office of Naval Research has generously supported me for many years, and I'm very, you know, happy that I've had the support and that I've been able to help solve some important problems for the Navy. And I've had many roughness collaborators some of whom are probably on this call right now. I know they are because I've highlighted a few already. And with that, I will stop and take some questions.
Thank you very much, Karen. It was a fantastic talk on roughness and where we are going. Maybe I'll start off with maybe something that's been bothering me for a while, which is when we have sort of patchy roughness, like the one that you had in the biofouling thing with the specimen that you have. I mean, does the pressure drop in a channel actually represent skin friction drag, the frictional drag of that kind of surface?
Well, does the pressure drop actually of that? I mean, I guess because you think the pressure drop is so local, is that your question?
Yeah, I mean, whether that is actually representative of that
the entire
condition,
surface,
or yeah, or if it's something that's just so happened there.
Yeah, it's a very good question. I mean, that's our problem with patchiness, is we assume that what we're getting is a representative answer, and we're not necessarily getting that. So I would say, you know, I don't know. And I'm hoping maybe to answer that a little bit with the patchiness of the other one that I'm working on, because that will be kind of the same patchiness, just the same random distribution through the whole thing. But again, you say I'm right over that one spot, right?
Yeah, okay.
Well, we have the ability to measure at multiple locations the pressure drop. And so I think that would be the best thing for us to do, is not rely, we're not relying on one location of pressure drop, multiply 3 or 4 locations in the channel and see how that changes. And that would be a very good, a good test of this.
Okay, there is a question from Ricardo Garcia Meral, who says, for the case of the slime, to what extent is it rigid roughness versus some kind of compliant surface?
So that one was possibly mildly compliant. We've tested other ones that I haven't shown here today, that where we had grasses that were flapping around, and that's a whole nother mess that I haven't shown. But I would say these were not perfectly rigid, but they also I don't know. I don't have a measure of the rigidity. It could have easily had a little bit of compliance to it as well.
Okay, so the next question is actually from Ian Castro, which says, do you think that the sort of atmospheric boundary layers, which is in urban type flows, has any essential differences from the kind of surfaces that you've been looking at?
Ian, I would say no. I'm hoping that we're addressing both issues, right? Trying to get to something that might look like that. There's, buildings and cornfields, and this doesn't look like a building or a cornfield. I just put this up, but the buildings and cornfields and ocean waves, and it's all kind of a different thing. But I think that if you kind of address the idea that if you can get statistics of that region and it's going over that region fairly homogeneously, then I think it applies. The whole issue that comes is if we can do this for a homogeneous surface, what happens when it's patchy, or it has strips of cornfields and with next to fields of soybeans, and then another cornfield, then another soybean, then we've got this kind of spanwise inhomogeneity that's going to create some secondary flows and create some messes. But I think there's a lot of atmospheric conditions where you had a long fetch of what the same roughness was that this would apply to.
There's another question which is about the lower limit of roughness to boundary layer thickness, below which, at what point does roughness not matter anymore?
Yeah, that's an excellent question. And, basically it changes for every roughness. The point you see where it matters is where it pops off from being hydraulically smooth. Okay, so this one here, at this roughness we had here, it came off a little bit earlier for KS plus. The other ones hung on a little bit longer. All right, it's really dependent upon the roughness and what's happening, I think, with the near wall flow structure in that roughness. It's not known. But I would say the one thing I do want to highlight, and maybe I can find a different slide to show you this. No, it's going to have to go back a little bit, is none of these display a Colebrook type roughness function, which is actually used on the Moody diagram, where you instantly have at any roughness Reynolds number, you have a roughness effect. Basically, you're transitionally rough from the get-go. Okay, and I think it's important to note that they do kind of stay hydraulically smooth. Some surfaces stay very hydraulically smooth for a while, and they don't display that kind of Colebrook roughness function. That we're actually seeing that more surfaces display kind of a Nicarazzi type roughness function, basically, where it waits for a while before you see a roughness effect. So my answer is, for every single roughness condition, it depends.
Okay, there's a question from which says, is there any scatter in the results due to different realizations from a roughness function with a given set of statistical parameters?
Yeah, that's a good question. Yeah, we tried to show, I think on one of these I show basically what the no, it was on the other one. Is there one? Well, we take an average over 6 basically runs. This is an average. I think there is some difference. I very much try what I do when I make the channels, the plates and the channels, is the channel is covered with plates that are different but have the same statistical distribution. So instead of printing up one plate and just repeating it down the entire length of the channel, I print up 6 different plates and I rotate them and I mix them up, and I make sure that there's not one kind of statistical distribution the whole way. I actually make a whole range of them and I mix them and I get it, because what I'm a little worried about is that if I had one plate and it had one hot spot or one high peak or something, then I would keep kind of triggering the flow to that one thing. So I purposely make a lot of distributions. So it's not the same surface the whole way down, but that surface has the same statistical distribution. I hope that answered that question, but I think there could be a variation, but we actually take 6 runs and average them. What you see is the results of the average of 6 runs.
Okay, there's another one which says, if the roughness in the propeller blades, are the roughness in the propeller blades checked and cleaned more often than in a kind of a ship hull? I mean, presumably it has a much bigger impact on shaft power.
I would have to tell you, I don't really know, but they should if they're not. I would think that maybe there's not as much, well, I don't know if there's much roughness as what's on there. I mean, part of the issue is actually getting divers down to look at it, to categorize it, and then to inform people to clean them. It would be much easier to clean the propeller than it would be to clean the entire hull. And I'm going to highlight some work real quick, just that I think is really important, that Mike Schultz and Nick Hutchins are doing right now. They're really looking at how do you manage the fact that a ship probably doesn't have the same roughness distribution on the entire bow to stern. So, and how do you average that over it? And I won't give you the punchline because I'm going to let them give you the punchline, but they've come up with an exceedingly clever way to do this. So look for that paper coming out soon. It's brilliant.
Closer to time. Maybe I'll have a final question, which is, so I mean, you showed some surfaces that actually doesn't have a fully rough.
Those are trouble. Those are.
How typical is it, and what do we do about them?
I don't know what we do about that. I mean, we've seen it for some of these biofouling surfaces. We've also seen it happen for very low slope surfaces. So I think it has to do with the fact that you're not getting, this flow separation, basically, that you have a surface that is kind of not creating ultimately some sort of really high momentum transfer mechanisms. So, we had these very shallow pyramids that we tested, and they also did this. I think it's the flow is kind of riding up over it and kind of meandering over it, and you're not kind of getting those classic kind of vertical motions of flow separation at a local level. And then it's a whole different can of worms.